Hello everyone and welcome to the Real-Time Embedded Systems lecture number 1, and this is the online version of the lecture that we just had together today on campus. So first things first, with the course meeting times. So on a weekly basis we'll be seeing each other on Tuesday, and then we have the on and off lectures. Those happen on Saturday. As prerequisites for this embedded system course, everything that you've learned in the CA, OS, and ESD courses are somewhat required in that particular course. And I've introduced you to your TAs, who are Walid and Loa. And then, as said in class, if you are interested, you can always read those references that you can put your hands on. But of course, I'm not requiring that you read them, but they're always interesting if you want to go the extra mile. However, all the notes that you'll be taking during the lectures, the physical ones and or the online ones, so anything that I'll be talking about and that is not necessarily written in black and white on the lecture slides are a definite material that you should be taking into consideration. The things that we're gonna tackle together in that course and the outline of it is the real-time paradigm and the embedded system concept. So what is it that we mean when we talk about embedded systems, and especially what do we mean when we say that we have to respect some real-time constraints. Later on we're gonna find out what are the different aspects of embedded systems, hardware wise, and then again from a software point of view. And this brings us to the one important software that we tackled last year, which is the operating system and the system software. And this year, as I told you before, we'll be tackling real-time operating systems, and particularly the free RTOS, which is an open source operating system that is meant to run on embedded systems. Later on, we're gonna talk about communication between the different embedded units, and this happens using embedded buses or embedded networks, and we're gonna tackle those as well. And I'm gonna introduce some challenges that are facing the real-time embedded system domain, such as security, dependability, autonomy, and other stuff. Most importantly, stemming from my own professional experience when I used to work at the French car manufacturer Renault, we're gonna talk a little bit about different things and standards stemming from the automotive industry. So we're gonna talk about the computers that are in cars, and we call them ECUs, and this stands for electronic control units. And I'm gonna introduce a couple of communication standards and some open architecture that is widely used in cars, and such as AutoZar. So basically, if you want to apply to internships or jobs in the automotive industry today, one recurrent keyword that you'll be seeing in most job offers is a knowledge of AutoZar and some communication networks such as CAN, etc., etc. when it comes to the tutorials now, know that you're gonna get your hands dirty, and this is one major transformation that I did to the course. I wanted it not to resemble to the microprocessor course anymore, and I wanted to be more industry oriented, because at the end of the day, this is what we're gonna be asked about when you're gonna do job interviews, and this is what you're gonna use in your everyday professional life later on as engineers, should you choose to work in the embedded sector, most precisely if you want to work in the automotive sector, or even aeronautical one, because they are extremely close to each other. So we've seen FPGAs in my DSD course that I delivered once here at GUC, and I'm not taking care of that anymore. So what you're gonna do using the FPGA, you're gonna create a virtual, if I'm allowed to call it this way, or more precisely a soft processor that will run on the FPGA, and you're gonna do that during the tutorial. And then you're gonna manipulate the Arduino or the Atmega microcontroller that is on the Arduino boards, and then you're gonna run the operating system, the real-time operating system, on the Arduino after testing it and using it on a desktop computer. And then you're gonna get to the communication section, and of course you're gonna do some exercises and case study, real-life case studies that are extremely interesting for you to try and analyze them as real-life engineers would do, and they had done it in during their career. You can always download some legal and free software tools, for instance in the automotive industry, from Vector. Vector is a German supplier, and they created some tools such as Canoe, and this is used in order to observe what happens on the embedded networks, especially the CAN bus in a car, and see the different messages that transit between the different computers with the different values and attributes. And we're going to talk about those things later in the automotive section as an illustrative, real-life illustrative example for this course. So the first thing that comes to mind when we talk about computers to non-engineers, and especially the people who did not take the CA course with me, the first thing that they can imagine is something like that. So a desktop computer, or a more fancy laptop computer, and some gamers out there can imagine that as well. However, shockingly enough, you're gonna find out that there's a number of computers in different objects and systems, and we were not expecting that. So first thing first, as an example, here we're talking about a particular system, which is the Apollo mission modules. So Apollo 11, and it was the mission that landed the first man on moon in 1969. And what we're looking at here, and for your info, everything has been declassified by NASA, and it's available, openly available for free for everyone on NASA's website. So what you need to know is, in order to guide the system, those two modules of Apollo 11, we needed only one computer, and this computer is called the Apollo Guiding Computer, or shortly called AGC. And the characteristics of this computer is that the words of the computer were 16-bit long, and it runs on a 2 megahertz clock. So you can Imagine that the processors that you have in your smartphones today, or even in any gaming console that you might have, or even the old ones, where even a, you know, have a better clock speed and wider words. So with only this particular computer, which is looked at today as not a high-end computer, we were able to take a moon from Earth, take a man from Earth to the moon, and then back to Earth again. Here, what we're looking at is typically what you can find under the hood of a car. And this is the infamous ECU, electronic control unit, I was telling you about. So it's a car computer, automotive computer, and you can find it here in your cars, for instance, under the hood. And if I asked you about the number of computers in a medium quality car, you'll be shocked to know that in average cars we have around 80 computers. That's a lot of computers compared to the one computer in the space shuttle that we've seen in '69. And if we go to the high end of cars, we will be having more than 150 computers. And as an example, I gave you the spec of Tesla, when you can see the different functionality in a car and the number of sets and CPUs, so computers or processors, that are up and running in the car in order to provide the different functionality here. And I've asked you to notice something, that the biggest number of sets of computer sets that we have is for the battery submodule system. This means that it's an electrical car and it's a Tesla, so yeah. And we can see how complicated and it's how complex it's to manage the battery system. How so? Because we have 16 sets of CPUs, so a total of 16 computers in order to manage the battery system in a car. And then we can see the number of computers everywhere with the rise of smart homes, smart cities, and the smart X paradigms. So embedded systems are ubiquitous, they're omnipresent, and they're everywhere. One particular project that we are working on currently in the IoT lab, a cluster of students and myself, so senior students and myself, are working on a smart autonomous bike, and notably an advanced rider assistance system that will help the rider to identify, for instance, the blind spots, and to help them avoid potholes, and to help them, get the bike from a parking lot in an autonomous and automated way, and back from the rider to the parking lot in an automated way as well. And we're still looking for junior future engineers who would be interested in that project and motivated to work on that project, even though you feel that you don't have these skills, because after your embedded system course you should have the necessary skills in order to be able to perform in such a cluster. But for the time being, we're taking you under our wings as under our wings as apprentices. So the first thing that we need to answer in this lecture is the following question: is what are real-time systems? And in order to be able to answer that question, we need to identify what do a nuclear plant, a stock market, and a simple MP3 player or iPod or whatever that is have in common. So we can notice here, for instance, in a nuclear plant, that if we want to halt the whole nuclear reaction, and you have the big button, the big red button. If you want to halt everything, all you have to do is push the button and expect the whole system to stop ASAP. Same thing in the stock market. If you're trading stocks or doing some exchange, monetary exchange, well, you're expecting to have on time new values and updated values whenever you're trying to solicit those new values. And same thing using an MP3 player. Whenever you want to listen to a song, you push the play button and you expect the song to start playing. So yeah, we can see that there's some notion of period of time that need to have an information ready or some action ready in respect to that particular period of time here. And to be more accurate and give it a formal definition, we can say that a real-time system is any information processing system. So it's another name for a computer. So it's any information processing system that has to respond to some stimuli, and this stimuli is usually some input from outside, so externally generated input stimuli within a finite and specified period of time. And see here, specified period of time, this throws you back to the OS and the CA courses when we talked about deadlines, for instance. So here in real-time systems there are some deadlines that need to be met and respected. In the literature, however, we're going to see that there are a couple of different subtypes of real-time systems. We have the soft ones, the firm ones, the hard ones, and the weakly hard ones. And what I've explained is the soft real-time systems are usually systems that, or where you can afford to have some deadline overruns. You can afford it, so they can be tolerated. However, they're definitely not desired, because you can afford them because there's no catastrophe that will be a result of missing deadlines. However, there's always some cost associated to overrunning deadlines, and it's often connected to something that we call quality of service. So basically, it will give you an indicator of the more deadlines you miss, the less quality of service you have. And I let you imagine a couple of examples during class. So these are the soft real-time systems. Now, when I look at the firm real-time systems now, it's not about tolerating and affording to miss deadlines. Here, if your job is not finished on time, so basically if you do not meet your deadline, so the computation result is obsolete. It's not useful anymore. And you can see that sometimes if the result is obsolete or not useful anymore, well, you can see that you'll have to do it again one more time or repeat it. So the cost may be interpreted as loss of energy that you'll be spending in doing things again, or some time that you'll be losing in order to to deal with this situation, or even some money that you might be losing. And the examples that we imagined together during the lecture of such firm real-time systems are the GPS system that you could have in your car. So basically, if you're going somewhere and the GPS lady tells you that you should have taken the exit from 200 meters before, so the information that the GPS is telling you is not useful anymore. It's obsolete because you've already missed your exit. And on the other hand, if you're trying to find out what's the weather like in Paris and you're taking your flight from Cairo, and then the information about the weather arrives when you get to Paris itself, and it would be unuseful because you didn't know that it's raining out there, so you didn't take your umbrella. This brings us to the hard real-time systems and the weakly hard real-time systems. And as a comparison, both systems are considered to be safety critical. So basically, here you cannot afford to miss deadlines, because a deadline overrun might and will lead to a catastrophe. And by catastrophe, I mean loss of lives or human lives or a huge damage. However, engineers, in order to make things easier to implement and more pragmatic, they've created the paradigm of weakly hard real-time systems, where you have some kind of fixed number of deadlines that you should meet, right, in order to avoid the catastrophe. And in those systems, you have some probabilistic guarantees, and those are sufficient to be able to avoid catastrophes. So in hard real-time systems, you need to meet all deadlines. In weakly hard real-time systems, you can afford to not meet a couple of deadlines, but you're gonna try your best not to and meet them all. Then we imagined during the lecture the different real-time systems that are hard, and we've seen that the pacemaker is considered to be a hard real-time system because you cannot afford missing deadlines. Some missiles, so the guiding systems or the explosion controller that might have been in this missile, for instance, it needs to meet the deadline and not run quickly or slowly, so it hits the target and and avoid a catastrophe. And anything related to medical drones or something like that, where you cannot implement redundancy because you cannot afford, you don't have neither the space for it nor the energy. So basically, these are strict hard real-time systems. And in the weakly hard real-time systems, we have airplanes, automobiles, or even trains. And here usually you have enough redundancy and dependability paradigms implemented that will allow you to miss some deadlines while guaranteeing the safety of the systems. However, one can notice that sometimes accidents happen, and they sometimes stem from errors and faults in those systems, and this is because of not respecting the deadlines and not being able to be resilient facing those deadlines. So the system failure happens even though they are weakly hard real-time system with redundancy. Now that we've defined what real-time systems are, we have to define what embedded systems now. So we've taken our time analyzing the different pictures that we have here, and we've seen that in those systems we have a lot of embedded systems. So what's an embedded system? We can see it as a small computer that is present in a bigger box or in a bigger system, right? Anything from TVs to printers, cars, airplanes, gaming machines or consoles, robots, etc., etc. So if you wanted to have a formal definition of an embedded system, that would be a computer system, right, that is part of bigger one, so part of a larger system, and that it interacts with the environment, right, and often with real-time computing constraints. This means that we have some kind of deadline that we need to respect in embedded system, and this is why we often in the literature talk about real-time embedded systems. So whenever we talk about embedded systems, we also mean real-time embedded systems. Here I'm giving you some figures from 2008, and this is where I personally entered the embedded system domain in the job market. That was my very first job in 2008. And back then, the figures of the previous year, which was in 2007, there were over 4 billion, that's 4,000 million embedded processors that were sold. So, you know, it's a huge number of computers considering the world's population. And I don't even want to look at the financial aspect of it. I'm more interested in the estimation from back then for 2020, and we're in 2020. So they were estimating the number of embedded processors to be 40 billions. 40 billion, that's a huge number, and back then we didn't even start talking massively about smart cities, smart homes, and smart grids, etc., with all these buzzwords that use the smart prefix. So you can imagine that this number is extremely huge today. Most importantly, here we can see the different domains where you can find embedded systems, and one major domain that is still soaring, and whenever you're gonna look for offers in the automotive industry, you will definitely see a lot of demand for embedded systems, embedded system engineers. So yeah, in the automotive industry, this is one of the whether it's the autonomous or the classical ones, you're gonna find that there's a huge number of computers that are still being used, and a lot of challenges to be tackled, such as migrating from mono processor to multi-core systems, and how to synchronize to guarantee deadlines, etc. And the research and development in this particular area is quite demanding. One of the last things that we covered in today's lecture were the different constraints that are related to embedded systems, and you can imagine them, because remember, so when we talk about real-time embedded systems, there's always the real-time paradigm that is respecting deadlines. So one of the first constraints that we should know of is definitely the time-related constraints, and we have to fulfill execution on strict timing. Whatever strict is whatever is meant by strict, it could be more or less flexible, considering that if it's a soft real-time, firm real-time, or hard real-time system. However, there are always deadlines that we need to take into considerations. Another thing that we identified together in today's lecture was the fact that we have limited and scarce resources when it comes to embedded systems. How's that? Because on a plane, for instance, you do not have unlimited power or energy. You don't have a lot of space to put your computers and the wiring, etc. Plus, each and every time you add components and you make the bigger system heavier, hence it will consume more energy. So there are a lot of trade-offs and a lot of constraints that need to be taken into consideration. And then there's of course the power dissipation, the heat dissipation, etc. And last but not least, there's no or minimal user interface, because usually the embedded systems are not meant to interact directly with the human users, unlike a desktop computer, for instance. So basically there are specified tasks and specific tasks that should run on those embedded systems, and they usually deal with sensors, actuators, and other embedded systems as well. And this is what we'll be talking and tackling throughout the whole embedded system lecture with me this year. One of the things you're gonna be dealing with when you work designing embedded systems is definitely to know how to make trade-offs when it comes to selecting hardware and software. And this is one of the most important jobs for you as engineers in your real life, is to know how to give the best optimized and functional, albeit a cost-effective solution. So yeah, it's a quite challenging task for people to make a trade-off, and usually this is what the real-life example that I've given you today was about the safety when it comes to airplanes, for instance. And you should know that we do not, companies do not do full tests, in the sense of they cannot prove that the system is fault-free, but they do their best to say that it's good enough to be functional. And because if they take their time in order to implement a fault-free system that is fully tested and perfect from a pragmatic point of view, it will take ages to create such a system, and second, if possible, it will take ages, and second, it will take a lot of money, and it will cost a lot, and hence it wouldn't be a cost-effective solution, in the sense of you won't be able to sell those airplanes and to make the industry work. Another design issue that you'll be dealing with is, should you decide to work in this domain, is how to deal with the distributed computing. So last year we talked about distributed computing in the OS and in the CA courses. So how to deal with parallelism, how to do some load balancing, and how to synchronize between the different cores that are working together in order to provide some functionality. This should take, of course, into consideration the temporal behavior. So hence we have to have some kind of correct representation of this behavior, because deadlines, they are crucial when it comes to real-time embedded systems. And one thing that you've learned in the CA course last year is definitely how to understand the different layers and transformations that happen from a high-level language all the way down to machine code. So you should take that into consideration when you're evaluating the real-time implications, especially in those deadline-oriented embedded systems. One of the major issues here is how to deal with fault tolerance, meaning that, and reliability, dependability, reliability, resilience. There are so many words in the jargon, but to make a long story short, fault tolerance is all about making sure that even if some error or some fault happens in the system, the system will keep on providing the service, even though it could be a reduced service or a minimal one. However, it should be some kind of resilient to the fault, and make sure that, for instance, if it's a plane, make sure that the voyage can keep on going and the plane could land safely in its outbound airport, for instance, or destination airport, or whatever that is. Of course, how to design and administrate tests. A lot of work needs to be done when it comes to the selection of testing, and because we cannot test all the scenarios, so there should be a lot of work on the selection of the tests. And then again, to be able to make people collaborate together. So I'm all in favor of open systems in opposition to closed systems, where we can have different people with different groups contributing and collaborating with each other in order to make the system work anywhere, everywhere, and could be compatible with different other systems. So this is what we call a system being interoperable. Then again, and I cannot stress this enough, it's all about predicting the response time, how much time would take the system to give the result, and in difference with what we've learned last year in the OS course, most probably, and a lot of time in the embedded system paradigm, response time is equal to the turnaround time. So we're more interested in when the whole task is done, instead of just when the task is starting to be executed. So it's extremely important for you to understand the difference. So here, response time in the context of embedded systems is definitely the turnaround time that we've learned last year. And then, in order to do that, we need to, from a theoretical point of view, study the schedulability of the whole system. So we're going to do some analysis, and we need to make sure that a priori, this means before runtime, we're satisfying the deadline. So we would be able, from a theoretical point of view, say that if everything goes well, my system is at least supposed to respect the deadlines. But you're gonna see that on runtime, at runtime, you will have some things happening that you were not expecting, or you have to deal some uncertainty that you're never really sure of, and it goes way beyond the scheduling theory. That was the last slide that we've seen together today in the lecture hall. I didn't have the time to talk about it, but whenever you're working on the design and modeling of RTES, so real-time embedded systems, the different layers. The first one is to define what your system is supposed to do using some informal language, some informal requirements described in a natural language such as English, French, or whatever. And then it's all about high-level algorithms and some texts. So these probably stem or come from upper management, where they say, let's take an example from the automotive industry, for instance. We could have the CEO or some project manager in some department at the OEM, so original equipment manufacturer, saying that at the Salon de l'Auto, and this is the exhibition when you have different car manufacturers, car makers, present their novelties on a yearly basis at the Porte de Versailles in Paris, for instance. you can have your CEO or boss or project manager telling you that I've seen an extremely interesting functionality in the new, I don't know, Porsche, in the new Peugeot, some car. So let's say it's a flickering headlight or some, I don't know, some adaptive cruise control back in the days. And then your job as engineers is to take those informal requirements and somehow map them to some text that is readable by you, by the other engineers and technicians, and some kind of algorithms. And then you go to step number one, where you need to divide them into functional and non-functional requirements, meaning that what are the different functions that should be implemented in order to have that big functionality. And then there are some aspects that come to non-functional, meaning that they could be related to quality, to respecting some standards. So for the let's say the adaptive cruise control, for instance, the functional requirement could be make sure to respect the mileage, or the what do we call it? The speed, the velocity. Make sure that you're respecting the road lanes, making sure that you're respecting the safe distance between two different cars. It could be, you know, a lot of driving aids and the cruise control, for the cruise control. And then it could be the non-functional requirements could be, well, the light could be blue or red, or something that is visually friendly, not aggressive, stuff like these. And then the last step in the whole process is to kick off the development. It could follow different schemas, such as a spiral one, a V one. It could be an agile one. There are so many things that are implemented or used in industry in order to uh, you know, have the development process ongoing. So this is pretty much it for the first lecture, and